All right, video for section 1.1, which is the start of Unit 1 or Chapter 1, AP Precalculus. First, an example just before even section 1.1 starts, an example to kick off the entire chapter. Not a problem, just like an example of how the stuff in this chapter can be relevant to the real world. You know, one of the central principles of economics is that the value of money is not constant. It is a function of time. Since fortunes are made and lost by people attempting to predict the future value of money, much attention is paid to quantitative measures like the Consumer Price Index, a basic measure of inflation in various sectors of the economy. Chapter 1 Overview. AP Precalculus is a course about functions. There are multiple representations and the many ways they can be used to model behavior in the real world. In this chapter, we begin the study of functions that will continue throughout the course. Your previous courses have introduced you to some basic functions. These functions can be visualized using a graphing calculator, and their properties can be described using the notation and terminology that will be introduced in this chapter. Familiarity with this terminology will serve you well in later chapters when we explore properties of functions in greater depth. So here we go, section 1.1. Scientists and engineers have always used mathematics to model the real world and thereby to unravel its mysteries. A mathematical model. So in this chapter, and I guess the whole course, we're going to be using the word model a lot, at least the textbook does. A mathematical model is a mathematical structure that approximates phenomena for the purpose of studying or predicting their behavior. Thanks to advances in computer technology, the process of devising mathematical models is now a rich field of study itself, mathematical modeling. In this class, we will be concerned primarily with three types of mathematical models. Each type gives insight into real-world problems, but the best insights are often gained by switching from one kind of model to the other. So what's like, you know, more like you'll start to see what it really means by talking about these models as we go through this section in this chapter and stuff. So numerical models. A numerical model is a mathematical model in which numbers or data are analyzed to gain insights into phenomena. So pretty simple. I don't know how much I want to elaborate on that right now, but like if you were trying to analyze, let's say, a function, a mathematical model or a numerical model would be like a table of values, you know, numbers, data, that to represent, you know, what is going on in your situation, the phenomena. So here we go. Example 1, which is about tracking the minimum wage. Might be a little too early to do that. Sorry. So we have a table here about the minimum hourly wage where we have year by year by year, and depending on the year, the minimum hourly wage, so basically minimum wage, and then the purchasing power in 1996 dollars. Okay. So question A. In what 5-year period did the actual minimum wage increase the most? So that would be like, what was it, from 1955 to 1960? Did we have the biggest increase, or from $1 to $1.25? Was that the bigger increase as we increase which one had the biggest increase? Well, if you just kind of analyze all the different increases, you would figure out that it was 1975 to 1980, because that was a whole $1 increase of the minimum hourly wage. In what year did a worker earning the minimum hourly wage enjoy the greatest purchasing power? Well, all you got to do is, that question really just means you need to look at this list and find the biggest one. So 1970, because someone earning the minimum hourly wage had a purchasing power worth $6.47. Question C, a worker on minimum wage in 1980 was earning nearly twice as much as a worker, so from $1.60 an hour to $3.10 per hour. And yet there was a great pressure to raise the minimum wage again. Why do you think that was? Why do you think there was even though it was the biggest increase in 10 years or whatever, or nearly, it was a big increase, like twice, but I mean, look at the purchasing power. So the purchasing power actually dropped by 57 cents. Why? Inflation and whatever. Example 2. We have another table of numbers. Remember, these are like kind of a numerical approach, so you're just kind of going by numbers and tables and stuff. Table 1.2 shows the growth in the number of prisoners incarcerated in state and federal prisons at year's end for selected years between 1980 and 2005. Is the proportion of female prisoners increasing over the years? So they're specifically asking, is the proportion increasing? Not the number of female, because that's really obvious. Like in 1980, there was like 13,000 incarcerated females, and then 23,000 5 years later, 44,000. So, but is the proportion? So that means we essentially need to add another column to the table. So down here in table 1.3, we'll do the percentage, female percentage, which is basically the proportion, okay? It's the same thing essentially. The female percentage, is that increasing? Is the proportion of female prisoners, or the percentage out of the total? Because the males are also going up too. So we're going to see if the percentage or proportion is increasing. So the female percentage. So in 1980, you'd have to do basically 13 out of, so it's like 13,000 out of the grand total of 329,000. So that'd be if you do that division, that's all you really need to do to get a decimal. And when you change that decimal to a percent, just by moving the decimal point over 2 places. So in 1980, females accounted for 3.9%. And just to kind of fast track this, if we kept that going, 23 out of 502, 44 out of 774, 68 out of, it's really the fractions or the percentages. And once you do that, okay, then yes, it's clearly the percent or the proportion is also increasing. All right, but that was different. It didn't have to be, if the males were increasing, more at a larger rate or whatever, then this would not have been a yes. But so number 2 is, algebraic models. Okay, so we have numerical models, and now we're looking at algebraic, which is a model that uses formulas or like equations, like, so an algebraic model or like an analytical model that essentially involves equations as like your main focus, equations, expressions, or formulas to relate variable quantities associated with the phenomena being studied. So a quick example like that, just that technically falls into an algebraic model. Pizzeria sells an 18 by 24 inch pizza for the same price as its large round pizza, which has 24 inches diameter. If both pizzas are the same thickness, so if that's not a factor, like the actual thickness, which means there'd be like potentially more pizza, because whatever, more volume of pizza. It's a funny way to think about pizza. How much volume of pizza did you consume? Which option gives the most pizza for your money, the most bang for your buck? Which option gives the most pizza for your money? Same price. Okay, so really all we have to figure out is like which one has the bigger area, right? So you'd set up some equations, or I guess really in this case you'd use the word formulas. You just have to remember the formula of a rectangle for area of a rectangle, and the formula for area of a circle. So maybe you can remember that, I don't know, but that's area, length times width is area of a rectangle, and the area of a circle is pi r squared, r being the radius, 24 inches, that'd be a diameter. So remember, radius is half the diameter, so that'd be like pi times 12 squared. Keep in mind, pi is just a number. It's an irrational number, but it's just a number. It's approximately what? Approximately 3.14. A lot of calculators, I'm sure the one that you might have handy right now, actually has a pi button, or a couple of buttons you can hit to get like just straight up pi on your but the approximation is 3.14. When you approximate the final answer, it's about 452.4 square inches. So the units of area, one example of that is square inches. How about the area of the rectangle? We're just doing like literally length times width, and so that is merely 432 square inches. So pretty obvious which one gives you the most pizza for your money. The circular pizza that has a diameter of 24 inches. That'd be more pizza, technically, than an 18 by 24 rectangle pizza, based on the analytic formula or equation. Exploration 1. If you want to do this just on your own, that's fine. We might not even do this in class if you were there. But just about designing an algebraic model, step-by-step exploration, maybe something to discover or like learn by doing, but let's skip that for this video. Probably skippable. So we can talk about graphical models. So a graphical model or a graphical approach, I'm sure you're probably guessing it, is going to use a graph. So not, numbers in a table, not the equation or the formula or whatever, but just like the visible representation of a model that gives insight into the relationship between variable quantities. Yeah, so just going by graph. Like sometimes you can find an answer by looking at the graph, rather than, working the equation or just analyzing numbers in the table. All right, so if you need to pause the video and finish writing that down, by all means, but let's go on to example 4, visualizing Galileo's gravity experiments. Woo. So Galileo spent a good deal of time rolling balls down inclined planes, carefully recording the distance they traveled as a function of elapsed time. His experiments are commonly repeated in physics classes today, so it's easy to reproduce a typical table of Galilean data. So that was a whole lot just to pretty much introduce this table that relates elapsed time in seconds to the distance traveled of a ball rolling down a ramp or something. Okay, so we're going by this table. What graphical model fits the data? Can you find an algebraic model that fits? Okay. Okay, I see what I did here. So step 1 would be to take this table that was given, and if we're looking to do like a graphical approach and look at this and see if we can figure things out graphically, we're just going to plot all these points. Okay. So it looks like the more like independent x variable would be the elapsed time, and then the more dependent variable, like the y vertical, axis variable, would be the distance. Okay, and so step 1 would be to pretty much like label up and scale up like the x-axis and figure out a scale and how to label up the y-axis. So like based on the number of boxes that I have you to work with here, and the number of boxes, and that we're going from like 0 to 8. Oh, let's see, 1, 2, 3, 4. I'm sure we can just go by ones here with like 1 second, 2 seconds, 3 seconds, 4 seconds. Here, we need to go up to at least 48, and so based on the number of boxes, 1, 2, 3, 4. I'm assuming we could go by twos. Yeah, I think that's what's happening. I didn't write every number, but every box is going by 2, like 2, 4, 6, 8, 10, 12, yada yada yada. So then once you have your x and y axis, or your horizontal and vertical axis, like kind of scaled up and labeled, now you can plot all these points like 0, 0. Look, 1, 0.75, or 75 hundredths, or whatever you want to. 2, 3, 3, 6.75. Basically, it'll end up looking something like this. Can you find an algebraic model that fits? Well, let's see, here we go. We're going to be seemingly pulling it, like anything from the past in Algebra 2 is going to seem like fair game, especially starting now. So you're looking at this graph. What kind of equation, what type of algebraic model? It's a fancy way to say, like, what kind of equation, what kind of function do you think like fits these dots? So hopefully you remember, graphing curves like this that look like a parabola, which would have been like a quadratic, function, a quadratic equation. And so it'd be like, something involving x squared, right? So what we do from here is we realize, okay, so like my equation is going to be like y equals something like some unknown number x squared. Okay, now stay with me here. Quadratic equations could also have like an x term, like a linear term, and then also like a constant term. So like you could have an equation that was like, I'll use different, like like placeholder, variables, like, because you might recognize literally y equals ax squared plus bx plus c. And you would just need to figure out what a would be for this particular graph and what b could be for this particular graph, or what seems to be this graph, and what c. But if you notice, and if you remember something else from Algebra 2, this appears like the vertex, at least it appears that we're like, the vertex is at 0, 0, And so since we know that the parabola is like sitting at the origin, we know that this is all there really needs possibly to be to the equation, just like something x squared, like there wouldn't be, for example, elaborate a little bit. Like there wouldn't need to be like a plus something, like plus t, or plus, I don't know, p, or plus m, because if there was like a plus something where it could have been like plus 2 or minus 5, like at the end of the equation, that means it shifts the parabola like up or down from the origin. You know what I mean? And similarly, there wouldn't be, possibly anything like, something x squared minus 3x, or something x squared plus 8x, because that would also like shift it, somewhere other than the vertex at the origin. So this is really all we need as like a jumping off point, and now it's just a matter of what is k? Based on these numbers and the graph and everything all together, what could we say k is? All right? And so all we really need to do, well, okay, this is just like, if I was, instead of using x and y, like I could use d for distance and t for, but it's the same thing. So all we have to do now, once we have it just simplified to just being like y equals some mystery number x squared, is maybe toss in like this one ordered pair for x and y, or for t and d, and then use that to figure out what that would make k. So we could figure out what k would be, just based on like this input and that output. And once you knew that k was actually 0.75, you could then write your final algebraic model or equation, for this graph. Okay? Again, pause if you need to before we're moving on. Just another example, if you want to pause the video and try this without me, you can go ahead and pause, but here we go. We showed an example 2, probably refers back to just like the textbook notes examples, that the percentage of females in the U.S. prison population has been, this is the notes. What am I saying? So referring back to example 2, you know what I mean? Literally in this same video, has been steadily growing over the years. Model this growth graphically and use the graphical model to suggest an algebraic model, or like an equation or something. Okay, is this the same numbers? Percentage of females after 1980. So it was 3.9 in 1980. Just making sure that these literally, yep. So in 1980, 3.9, 4.6, 5.7. All right, So yeah, it literally is from example 2. Okay, I just decided I wanted to confirm that. So basically, we're going to have to label this up. So so the independent or input normally goes on the so we have to go like 5, 10, 15, 20, 25 based on the number of boxes we have to work with, the grid. And then the F, the actual percentage of females over here, going from like 1, 2, 3, 4, 5, 6, 7. I probably just went by ones, right? Because we can. And then graphing all of these, like starting with 0, comma 3.9, ish. Then 5, comma 4.6. So that would be once you get the dots graphed. And so now you're looking at this and it's like, man, what kind of graph could fit those points, pretty good. And I'm looking at this going like maybe a line right through all these dots. And so what we would do is, once you kind of saw the graph and was like, looks like a line or, close enough, right? So as far as coming up with like the equation of that line, this definitely refers back to like Algebra 1 and Algebra 2 and maybe even before all that stuff, where you could figure out the slope and the y-intercept. Remember, y equals mx plus b. That's a form for like a linear equation. So as long as you know the slope of a line as well as its y-intercept, which is b, you can write the equation just like that. So here we're calculating slope, and definitely, using the last point and the first point, like that's a pretty good way to go about things. Like the farthest apart 2 points to kind of get a slope going. So remember, the whole formula for slope. Hopefully this looks familiar enough. So we end up with a slope of, hopefully, it's exactly 0.128. I guess it could be approximate, but it looks like, unless I just didn't think to, put approximately equal. It looks like it might be exactly 0.128. It's not very often you like to use decimals for slopes. Like slope is usually a fraction, but hey, you could do a decimal for a slope. That's okay. And then what's the y-intercept? If we have the slope, and isn't it like, clearly obvious what the y-intercept is by looking at the graph, but really looking at the table? So there's my equation, which if we were, so you're pretty much so, fixated, and that's fine, on, y equals, mx plus b. But here, just going clearly in the table, it was not technically x and y, it was t and f, which is just taking the place of x and y, so not that big of a deal. So I guess this might be like your final answer, utilizing the actual variables they have here in the situation. Exploration 2. Yeah, once again, if just for the purposes of the video, if you want to skip this, skip it or pause the video and take a look at that. The zero factor property, another thing hopefully you remember from like Algebra 2, but a product, which means multiplication, of real numbers is 0 if and only if at least one of those factors in the product is 0. If two numbers multiply to make 0, one of them or both of them has to be 0. So a couple more examples here. solving an equation. So in this case, algebraically, okay? Because there potentially could be like a numerical approach and there could be a graphical approach, but just like back in Algebra 2, we're going to try to solve this equation algebraically just by working the equation. So if you remember from Algebra 2, that's when they started giving you equations and solving to solve for x, like just a one variable, equation where you had to solve for the variable. So in Algebra 2, they started giving you equations that you couldn't just get x by itself. Like for 6th grade, 7th grade, 8th grade, whatever, you were just, all you had to really do was get x by itself. But in Algebra 2, it was like, oh, we can't just like get x by itself. So what was the next sort of like strategy? Well, that strategy involved setting the equation equal to 0 if it wasn't already set equal to 0. And then what? Setting it equal to 0 and then factoring. Okay? So it had to be 0, and then once it was all equal to 0, you would attempt to factor the left side. So in this example, that becomes like a GCF. So like if there's a GCF, you factor that out first. That's always the first kind of factoring that you try. And then, you always, after doing a GCF, you always check to see if this, like the factor that's that corresponds, along with the GCF, will this factor again by what a lot of people call unfoil, So we brought out an x, but can this 6x squared minus 11x minus 10, can that factor again by unfoil, or basically into two binomials? So this could be a whole like can of worms here that I could open up, but like long story short, some people can just, if it's possible, like if a trinomial is possible to like unfoil like into two binomials, you could potentially just do this in your head, like mix and match different bubbles where you could get like the 6x squared, the negative 10, that they would foil together to make this whole thing. But, I am very much like when in these situations, like I always do something called the Phoenix method. So this is the Phoenix method, where like you multiply the 6 to the other end, and then now you can do like some basic unfoil, what two numbers multiply to make negative 60, but they also add up to negative 11. So that would be those two numbers. And then the phoenix rises from the ashes, comes back to life, and then you take both fractions, and if you can reduce either fraction or both fractions, you do that. And once you do any reducing, if possible, you bump each denominator up in front of the x to get like a final factored form here of like the original GCF x, and then these two binomials of 2x minus 5 and 3x plus 2. So this is now fully factored, and so now once it's factored, what do you do next? So quick recap. After you've set it equal to 0, then you look to factor. After you've factored, what do you then do? Well, now you set all the factors equal to 0 separately. So including a GCF if it's there. So x could equal 0, that would solve it, or the 2x minus 5. factor could equal 0, and when you solve that one now, you end up with like, okay, so a final answer could also be x equals 5/2, and then or this 3x plus 2 binomial factor. So you set all the factors equal to 0, and then you solve them separately. And this one would eventually result in an answer of negative 2/3. Okay? So that was algebraic. So one more example with this equation, which again, you can't just get x by itself. So you're going to try to, get that equal to 0 followed by factoring. But if you remember back to algebra 2, not everything factors. So if you tried to like do a GCF, no, there's no GCF. If you tried to do unfoil, you can't. Like there's no there's no two numbers that multiply to make -10, but they also add up to +4. So remember back to algebra 2. What do you do to solve a quadratic equation when the whole factoring approach doesn't pan out? Do you remember that there was literally a quadratic formula that you could just plug everything into, and it would always work whether something could factor or not? Like the quadratic formula would always work. So remember how there was like an A value, a B value, and a C value that would get plugged into the quadratic formula? And so this one ended up with this. All right. And because 4 squared minus 4 times 1 times -10 ends up as 56. All right. Now, this answer is not probably the bestest final answer. This answer could, well, I guess first of all I'll say this answer could be approximated, like the square root of 56. That is not nice. It's not like that says the square root of 64 or the square root of 9 or the square root of 81 or the square root of 1 or the square root of 4. The square root of 56, that is a nasty, irrational number. Okay? So we could approximate this. And remember, there is technically two answers here. One answer where you go with the plus, like -4 plus, square root of 56 divided by 2. And then the other answer is when you do -4 minus square root of 56 divided by 2. And you could like approximate both those answers. Okay? But if the situation calls for exact answers, this is sometimes good enough, right? If you can do like nothing with the square root, like if it was the square root of 13 or the square root of 7 or the square root of 17 or not, whatever, the square root of 21, then you would just stop here. But the square root of 56 can actually be simplified, okay, not approximated, simplified. And I believe the square root of 56 will end up as, is 56 divisible by 16? It's definitely divisible by 4. 56 divided by 4, so just 4. So the square root of 56 could get simplified to be 2 times the square root of 14. Okay? And once this would be rewritten as 2 root 14, then you could actually divide the 2 into both the -4 and, the 2 that would get brought out for like a final answer. But just to kind of like, bring this video to a close here and wrap this up. You could also solve these things graphically. It's an amazing like cheat code, okay? Because you could take this equation like that, and it's got to be, again, set equal to 0, and you could kind of treat it like, instead of it all equaling 0, you could treat it like it was equal to y, like a whole other variable, the y variable, which if it was all equal to y, you could now throw this into your graphing calculator or desmos.com, which is what I have here. And the answers to this equation will show up on that graph, the equals y graph, as its x-intercepts. All right? Because remember, like, think back to Algebra 1, Algebra 2. Remember that, like, whenever you plug in 0 for y, it kind of reveals or it flushes out the x-intercepts. Like, if y literally equals 0, well, geez, you're talking about the x-axis. The x-axis is literally when your y-coordinates are 0. So just by graphing this as like it equals y, the answers, the solutions, whether nice or ugly, will show up as the x-intercepts. It's an amazing cheat code if you're allowed to use graphing technology. So we'll just leave it at that. It's obviously the end anyway, but that is section 1.1, AP Precalc.